We are now coming to a unit where you will learn something that is of especially high interest to industry: calibration and validation of DEM simulation models.
Let us now go into the details of verification, validation, and calibration. As always, we're going to start with what you will learn in this unit. First, we would like to highlight the differences between verification and validation. The reason is that these two terms are often confused. Second, we would like to answer the questions why and when one should calibrate the DEM parameter set. Next, we're going to provide an overview of the most important calibration experiments, and we will finish these units by the methods used for practical calibration tasks. If we look into the differences between verification and validation, we have to first gain an overview of what we are doing when we are doing a simulation. First, of course, we have the real system, reality. We will conceptualize or simplify, abstract the reality into a mathematical model. These mathematical models are then transferred to computer models. We do this by implementing a numerical code. If we're now talking about verification, our goal is to check whether this code implementation was successful or not. Of course, we can only do this by making a comparison between the computer model prediction and a precise, absolutely precise solution of the mathematical model. Such a solution can be, for example, an analytical solution of the mathematical model in a limiting case. For example, if we only consider two particles colliding. If we now look at the wording validation, we always mean a comparison between the real system, so an actual measurement, and the prediction of a computer model. So here we're trying to close the cycle between the real system, validation data, and simulation and experimenting that aims on depicting the real system. Let us now get closer into the topic of verification. Verification is used to confirm whether the code implementation of the mathematical model is working properly. Well, what does properly mean? We understand under verification that the computational result agrees to our semi-analytical or analytical solution within a few percent. As always, there's a trade-off between effort and acceptable error. Of course, if we further refine, for example, the time step of our DEM simulation, we will reduce the deviation to our reference, which is the analytical solution, but at the same time, the computational effort might skyrocket. In summary, verification means that we can only judge on the quality of the numerical approximation, but not on the model approximations. And the reason again for this is that we already started the mathematical model. What is important is that we verify each part of a simulator. This is very often called unit testing. For example, we have modified a contact model or have implemented a new contact model, and now it needs to be verified that it has been implemented correctly. This can be done, for example, in a so-called test harness. Let us now look at an example. Here we have used the hook stiffness normal contact force closure available in lights. This closure allows us to directly specify the stiffnesses that should be considered between the two particles in a contact. We have looked at the perfect elastic case, so coefficient of restitution equal to 1, as well as damped situations. So we have lowered the coefficient of restitution. What we would also like to highlight here is the switch limit force. We have discussed about this in the contact force closures, and limit force does nothing else as limiting the contact force in this case to be purely repulsive. More information about this test case can be found here. So let us now look at the results. This is an inelastic collision. You see the particles overlapping, and the vectors have illustrated the force acting on the two particles. We now look at the time evolution of this contact force. For the undamped case, the black solid line, we find a maximum force on particle number 1, the left particle, of minus 1.27917 e to the power of 4 Newton. If we look at the analytical solution, you will find that we made only this tiny error here. If we now employ damping, so we simulate a system with a lower coefficient of restitution than 1, you will see that there is a difference between the situation where we have limit force on. This is the red dashed line. You see here no overshoot, in contrast to the situation where we don't limit the force, where the gray circles here illustrate that you get a little bit of attractive force. So this is again a nice example of a quantitative and a qualitative verification of your implementation. Another verification data point that we should use is the contact duration. If we use the analytical solution for that, we will find that our simulation for the purely elastic case gives an error of minus 0.2%. Another example of a verification study is to track the motion of a light particle in a swirling liquid flow. So this is a test case for a CFD DEM simulation. What you see here is the result of such a test case for two different conditions. Here at a slowly swirling flow, and on the left you see the distance of the light particle to the axis of the swirling flow. So this is the axis location, and this is a unit distance of 1. You see that over time, in this case for a slowly swirling flow, the light particle is steadily approaching the axis. If we would look at the trajectory along the axis, so this is the view along the axis of the swirling flow, you will see a behavior like this. So the particle starts here and then rotates and slowly approaches the center axis. However, if the swirling flow is a little bit faster, so approximately 5 times faster, you will see this oscillating behavior. So the particle would start here and then essentially overshoot and then finally approach the axis of the swirling flow. This is a very useful test case because it allows to check a number of closures at the same time. Here, for example, that of the drag force, that of the pressure gradient force, and that of a lift force that is here also relevant. Let us now look into the term validation. We have seen that validation refers to whether the simulator can predict a real-life phenomenon or not. So the central question when you're doing validation is, do we have the right model? The key quantity to be predicted is, of course, an experimental result. This is often called the ground truth, the target, or the output. The choice of these key quantities is dictated by the experimental setup. The reason for this is obvious. We cannot measure everything in an experimental setup, but only certain quantities. In summary, validation judges on the quality of the numerical approximations that we have made and the model approximations. Let us now look into an example. Here we have picked silo discharge. The key quantity that can be measured and is easily available is the mass discharge rate, so the kilogram per second or the particle amount per second that is leaving the silo. And this depends on the opening width of the silo. Here you see the reference data, experimental data, the dashed line and the dotted line, and different simulations. The simulations here consider different softnesses of the particles. You see for this stiffness parameter alpha, that has the highest value, we can get very close to the experimental data for soft particles. In contrast, for the very stiff particles, where alpha is 0, our numerical approximation can give a good picture, but is certainly not perfect. That was it for this first part. I hope you enjoyed it. See you next time.